Good. All right, I'm Cam Arnold. So my 6-minute talk today is going to be about my senior design project. It's the calciner burner replacement tool. We're sponsored by Shell Catalyst and Technologies. Pictured there is the final SolidWorks of the device, which was finished yesterday. Nice. A little background information about the site itself. So Shell Catalyst and Technologies is a plant in Port Allen, Louisiana. They develop catalysts for the petrochemical industry. The calcination process is very integral into making these catalysts, which are helpful in chemical reaction processes. But they just mainly work in building and making these catalysts. Each of these sites have these large calciners pictured here. This thing extends a good like 50 feet, and they have multiple burner nozzles. They have 16 of them total in each of these calciners. Pictured here is a burner when it's actually installed and all the instrumentation is attached. Here is the burner nozzle that will actually be tasked with removing. As you can see back here, this is actually where the burner nozzle is. So before we actually go through and replace these or remove them, all this instrumentation will be put out of the way, so that's not under our scope of work. But project motivation, so why are we actually replacing these? So currently, they get replaced approximately every 2 years. This is due to them burning out within this calcination process. They use significant manpower, and it's a really dangerous situation with this limited working space. It's a very heavy device, being 162 pounds, which I'll get into in the next couple slides. And like I said, the burner nozzles crack. They do this to thermal stress, material selection, corrosion, improper install, vibrations, and chemical reactions. Here's the current replacement process. As I said, it's a very manual labor intensive process. It's a 3 to 4 person, it's supposed to be a 4-person job. OSHA says you can only lift 40 pounds per person. If you do the math, that doesn't add up to 160 pounds. So then the 4th guy is coming there at the end of that video. As you can see though, they have to lever it out. And it just takes a while and can cause injuries. So yeah, 4-person job, it's dangerous, it involves suspended load. So we're trying to minimize the manual labor in this process, which is what our problem solution does, which I'll get into in a second. But a previous design, which is by our sponsor as well, this was nicknamed the wrecking ball because this was actually 1,000 pounds and it was a suspended load. It's kind of hard to explain exactly how it worked, but it had a pin that was in the middle with this 900-pound counterweight on the backside. And you pull the pin and it would like mechanically pull back the nozzle out of place. It was used one time and it's been sitting in the junkyard since. So obviously that we're trying to improve on that design, and I think we have. So our current solution is this device right here. So a couple things I want to point out. The nozzle will actually get attached here. There are studs that are on the nozzle that will be bolted there, and this allows for 360 degrees of rotation within this as well if there's any angular deformities within the insertion point. There's a height adjustment mechanism which can be used just in case they install the calciner wrong. There's any height deviations there. We have a counterweight to make sure that this device is stable and that it won't fall apart or anything. We have an A-frame that will be used to actually stabilize the entire device as well. In terms of traversing the motion, we have a gear that will be used to go forward and back and in place, take it or put it into place and take it out of place. That will be driven using a drill. So yeah. But the whole process, so the crane will bring this device up to the platform, which is 40 feet in the air. It will place it right in front of the calcination burner hole point with the nozzle attached. The attachment bar will be retracted using a drill, removing the old nozzle. I said that backwards, but all right. The crane will then bring the device back down with the nozzle attached. They'll remove the old nozzle, attach a new nozzle. Do the same process. The crane will bring it up 40 feet right in front of the point, and then they'll advance it using the drill again, and then manually bolt it into place. So our objective overall is to use a mechanical device to safely and effectively replace these calciner burners. It should minimize the need for manual labor within this process. So functions, just go over. The main ones are attached to the crane. We want it to be stable. We want to minimize manual labor. We want to be safe first and foremost. We want to replace the nozzle. In terms of replacing the nozzle, we'll make sure we can attach to it and be able to rotate the nozzle and make sure we can line up the bolt holes. And then we want to support the load during static loading and dynamic loading. There should only be static though. In terms of traversing the nozzle, we want to make sure we can insert it and remove it. We're doing this with the rack and pinion with the gear. So analysis to be done, which we've been currently doing, free body diagrams, static analysis, safety factors, which their safety factor was 4, which is given to us by our sponsor, bending moment analysis, stress analysis, and all the legs and everything like that, gear analysis, welding analysis, parametric analysis to make sure that we can have the right dimensions, make sure we can handle all the loads, material selection, it's all going to be carbon steel, FEA, and then cost analysis at the end. Some safety hazards, like I said, the current process uses a heavy suspended load. They're working at heights, there's slipping hazards, back strains, pinch points. Our current device will not be a suspended load, it will be on the platform itself. It will reduce these pinch points and minimize manual labor. So those are covered there. Environmental impact, so during machining, there will be significant energy being used in the consumption and creating this product. So I want to make sure that we're mindful of that. And in terms of recycling, once it's done, I want to make sure that we're trying to repair all the different components, making sure that we're disposing of them safely. Like I said, our device is purely mechanical. There's not really any environmental impact there. I want to make sure that we recycle the metal waste once it actually does bite the dust in about 30 to 40 years. It's not going to be used that often. So. Preliminary schedule, so engineering analysis being done by the 20th. That's going to get pushed back till tomorrow, I think, but should be done by then. We're going to present our drawings by the 7th to our sponsor, and then they're doing it in-house, so we got to figure out the timeline for manufacturing and testing them. Whoever says any questions.
Hey, just out of curiosity,